Swayam Prabha. Digital India. Educated India.
Welcome back. So, in the last lecture, we just talked about the permeability in soil, and we have seen what for this permeability and how this permeability is coming into the picture in soil mechanics, right? And then we stopped in the last lecture about the when we were discussing about the factors affecting hydraulic conductivity. So, hydraulic conductivity depends on several factors as we discussed in the last lecture, that is fluid viscosity, because viscosity is dependent on temperature, and of course, the temperature will affect the permeability. So, pore size distribution, because permeability depends on the interconnected pore space, and therefore, pore size distribution is very essential to determine the permeability. Now, grain size distribution is another factor which will affect the permeability in a great extent. Then coming to the void ratio, of course, you know that as you increase the void ratio, of course, your pore space or the volume of voids will be increasing, and therefore, your permeability will increase. Then roughness of mineral particles, because the the particles whatever is present in the soil deposit, the roughness of the surface or the texture of the surface will greatly affect the permeability. Then finally, degree of saturation. Now, it is conventional to express the permeability or the coefficient of permeability K at a temperature of 20 degrees centigrade. So, this is the conventional procedure or conventional method to express K. However, if you want to obtain K, that is the hydraulic conductivity or the coefficient of permeability at different temperature, then you have to use this expression. So, K 20 degrees centigrade, that is generally expressed in the literature, which is equal to eta at T degree centigrade by eta 20 degree centigrade into K at T degree centigrade. So, that means if you know, so this is if it is known to you, this K 20 degree centigrade that is provided or that is supplied in the literature, then eta 20 degree centigrade, that means you, if you are dealing with the pore fluid as water, then of course, the viscosity of water at 20 degree centigrade you need to find out. Then the whatever temperature you would like to or you would wish to find out the coefficient of permeability. So, for that you need to find out the viscosity or you need to obtain the viscosity at that temperature, and if you know these three values, finally you can get the K, that is the coefficient of permeability at that particular temperature whatever you want. So, where eta is the viscosity. Now, we are coming to how to obtain or how to find out this coefficient of permeability or the hydraulic conductivity. So, there are several procedures as well, in laboratory procedures as well as you have the field procedures. So, first we will discuss about the laboratory determination of hydraulic conductivity. So, you have got basically two different methods by which you can find out the hydraulic conductivity. First one is the constant head test. So, here basically what we do, so this is your soil sample. So, this is your soil sample, okay, and on top of the soil sample you have one porous stone, and at the bottom of the soil sample you have got another porous stone. So, basically these porous stones will allow the water to flow through the soil body or the soil deposit, soil specimen, but it will not allow the soil specimen to go out, right, along the flow. So, it will act as a screener, okay. So, now what we do here, so we put the water on top of this. So, this is the water level and we try to maintain the constant water level at that surface. So, and this soil specimen will be resting on some tank, and this is the water level of this tank. So, therefore, this small h is the head difference between the entry level and the exit level, okay, and the L is the length of the soil specimen, and you are basically measuring. So you are putting the water on top of this. So water will flow through the soil specimen, it will come out below the soil specimen, and ultimately you have some outlet in this tank, and through this outlet basically you will be collecting the water in some graduated flask or some measuring flask. Okay. So that means you need to, I mean, what are the things you need to find out? So this head, basically you know what is the head difference between the entry level and the exit level, what is the length of the soil specimen, and how much water you are collecting, okay, in the measuring or the graduated flask. That means the quantity, okay, at some particular time. Okay, these are the things you need to observe in the laboratory. Now, based on that, the expressions can be derived like that. The volume of water collected at say time t is nothing but say capital Q, which is nothing but the area, that is A into V into T, that is the area of the soil specimen, into velocity, okay, the velocity of the flow, and the time t. So at time t whatever you are accumulating or water collecting. So where Q is the volume of water collected, A is the area of cross section of the soil specimen, small t is the duration of water collection, and I is nothing but the hydraulic conductivity, which is nothing but the head loss divided by the length through which the flow is occurring. So head loss is H, because that is the head difference between the entry level and the exit level. So that is nothing but the head loss in this situation. So H, small h by L will give you the hydraulic gradient I, and where L is the length of specimen. Now therefore Q can be written as A into, instead of I you can write H by L. So K into A into K into H by L into T, or we can write K, that is the coefficient of permeability or the hydraulic conductivity, is equal to Q into L divided by A into H into T. Now you can measure this, because you are observing that thing from the laboratory experiment. You can measure the soil specimen length. This is the cross section area of the soil specimen, that is also very typical, right, it is a standard one. And small h, that head actually you are maintaining, that is the head difference between the entry level and the exit level, and the time you are observing, that at what, I mean, that is the time at which you are collecting the water in the graduating flask. So if you know all these 5 parameters, basically you can find out your desired parameter, that is coefficient of permeability or the hydraulic conductivity. Now once we have seen the constant head test, now another test is falling head test. So there actually you are allowing the water head to fall from some height to some different height, okay. So we will see that. So this is the test procedure. Basically what we do, this is your standpipe, you have the soil specimen here, and again it is sandwiched between 2 porous stones, top porous stone and the bottom porous stone, and you are collecting the water through this standpipe at some measuring device, okay, some kind of tank, and this tank, I mean, this is your constant head will be maintained at the tank. Otherwise, I mean, if it is overflowing, then the water will go out. Now basically you see, so this is the water level at the exit level, okay. Now you are allowing, so before starting the test, this was your water level, and you are allowing the water level to fall down up to this level. So H1, small h1 was the level difference between the entry level and the exit level during the starting of the test, and during the finishing or the completion of the test you have H2, that is the head difference between the entry level and the exit level, okay. So now at any depth or any level difference or the head difference small h, and you can consider some incremental difference, that is dH. Okay. So now these are the things you can I mean this H1 is known to you because you are starting the test. So, you must know what is your level at the initiation of the test, okay. And this H2 is your final level difference between the entry and exit level after completion of the test. So, you know the length of the specimen, you know I mean other details from the laboratory experiment details available with you. Now, the initial head difference H1 is you are measuring at time t equal to 0, say, right. So, that is the initiation of the test, that is the starting point of the test. So, initial head difference is H1 at time t equal to 0 is recorded, and water is allowed to flow through the soil specimen such that the final head difference at the time t equal to T2, say at some time T2, the head difference, final head difference is H2, okay. So, basically at t equal to 0 your head difference is H1, and at t equal to T2 your head difference is H2. Therefore, the rate of flow at any time t is small q, say, equal to k into the hydraulic gradient, that is h by L into A, right, ki, that is the velocity, into A, where I is nothing but h by L, which is equal to minus A. So, I will define all those parameters. Minus A is the cross section area of the standpipe, okay, into dH dt, okay. So, dH is the incremental head difference of whatever we have just seen, and dt is the incremental time, where q is the flow rate, fine, small a is the cross sectional area of the standpipe, and capital A is the cross sectional area of the soil specimen. And the negative sign is coming because with time your head is decreasing, right. So, because of that you have got the negative sign before this expression, okay. So, rearranging the equation 1.11, basically we get dt is equal to small a into L divided by A, capital A into K into minus dH by H. So, now we are integrating both the sides over the range 0 to t dt and over the range H1 to H2. So, from this basically we are getting t equal to this. So, t equal to small a into L divided by AK into log base E H1 by H2. So, now from this expression I can get, this is my final expression, that is the expression which will give me the hydraulic conductivity small k, where this is known to me because you know the cross sectional area of the standpipe, this is very standard. So, if you go to the laboratory you will see that standpipe, you can measure the standpipe cross sectional area or the diameter of the standpipe. So, you can find out the cross sectional area of the standpipe. So, L, that is also very standard. So, length of the soil specimen, A, cross sectional area of the soil specimen, that also you can measure. T, basically you are observing at what time your head is falling from H1 to H2, and H1 the head difference at the starting level that you can record, and of course H2 you can record at the finishing of the test or at the completion of the test. So, if you know all the parameters you can find out the coefficient of permeability or the hydraulic conductivity. Now, there are several empirical relations available in the literature to find out hydraulic conductivity. I will go one by one. So, for fairly uniform sand, Hagen in 1931 proposed an empirical relationship for K, which is given by K in centimeter per second is equal to C, some constant, multiplied by D10 to the power 2, that means C D10 square, where C is a constant which will vary from 1 to 1.5, and D10 is nothing but, as you know from our earlier discussion, that effective size in millimeter. So, please remember the unit because this is the empirical equation. D10 is expressed in millimeter, whereas K is expressed in centimeter per second and C is a constant. So, Casagrande proposed another say empirical equation, proposed a simple relationship for K for fine to medium clean sand. Okay. So, these empirical relations are suitable for sandy particles or the granular material. Now, K, as per Casagrande, K is given by 1.4 into E square into K 0.85. Now, what is K 0.85? Now, let us see, where K is the hardly conductivity at a void ratio E. So, now suppose you have got some sand, so you can find out the void ratio. So, at that void ratio, basically you need to obtain, or you wish to obtain, the hardly conductivity. So, at that E, or the corresponding to that E, basically you want to find out K. Now, you have to find out K 0.85, which is nothing but the hardly conductivity or the coefficient of permeability at void ratio equal to 0.85. So, at the same sand, basically you obtain the hardly conductivity from some laboratory experiment at this void ratio E 0.85, and the whatever void ratio is available with you actually. So, corresponding to that void ratio, you can find out K from this expression. Okay. So, this is very simple expression, only thing is that you need to find out, say, K 0.85 from the laboratory experiment. Now, one thing I would like to mention as we are discussing about this sand and all. Now, from the laboratory experiment, you have seen two kinds of laboratory experiment, right? One is your constant head, another one is your falling head test. Now, as you know from your own experience, that if you put water on top of sand, then it will seep through, or it will percolate through the sand body immediately, right? Whereas, if you put water on top of clay, it will take some time, okay, to percolate through or seep through the soil body. Now, basically these are two things which will govern, or which will tell you that what type of test will be suitable for what type of soil. Now, if you think about the constant head test, basically you are maintaining the constant head. Now, if your flow through the soil is not good enough, if your flowability or the permeability of the soil body is not good enough, then you will not be able to maintain the constant head. So, that means you need to have some higher magnitude of coefficient of permeability, so that you can maintain the constant head. So, therefore, the constant head will be always suitable for sandy type of soil or the granular type of soil, because the water percolation rate will be very high and you will be able to maintain the constant head. Whereas, in case of cohesive soil, that is, I should not say cohesive soil at this moment, because you are not familiar to this term cohesion. Anyway, but clay type of soil, if you consider, or fine grained soil, where the permeability is very less, because as you know from the grain size distribution, the granular material will allow you more drainage or more seepage, whereas the fine particles or the fine grained soil will give you very less amount of permeability. So, now what exactly you are thinking of? So, if you choose the clay soil, and if you want to find out the hardly conductivity in the clay soil, then basically you are putting water, and that water, that seeping of this water through the soil body will take some time, right. So, you will not be able to maintain the constant head for that, because the permeability is very low. So, you are putting some initial head and you are allowing the water to seep through, and then you are observing some final head. So, therefore, for this fine grained soil, particularly clay type of soil, you should use the falling head test to determine the hardly conductivity. So, for granular material you will be using constant head, and for fine grained soil you will be using falling head. Now, coming back to the empirical equation once again, that Kozny and Karman propose that K is proportional to E cube by 1 plus E, where E is the void ratio, or K is equal to C1, that is some constant multiplied by E cube by 1 plus E, where C1 is a constant which can be obtained by getting K at two different E values. So, at two different E values you choose. So, any soil you take, and then for different E values you find out the permeability, and then based on that you find out C1. So, once C1 is obtained, then you can find out K for any other void ratio. Okay. So, I will stop here today. So, in the next lecture we will continue with this permeability, and we will try to find out how to find out the permeability in the field and other different factors, like if you have the stratified soil, how the permeability or the equivalent permeability can be calculated. All those things we will be seeing in the next class. Thank you.